This podcast is sponsored by the Building Performance Workshop, where I create tons of home performance resources to help pros make more money doing better work for happier clients. More at buildingperformanceworkshop.com. Enjoy. Welcome to the Building Performance Podcast from Green Dream Group in Chicago. I'm Corbett Lunsford, and today we're talking about trends in high-performance building and retrofits from the air quality angle with Brett Singer, scientist. He is with the Lawrence Berkeley National Laboratory in the Air Quality Division. Brett, thank you so much for being on the show.
Hey, great to be here.
So you just, first of all, we're at the ACI Regional Home Performance Conference in California, and you presented 2 out of the 3 sessions today, and you're going on very little sleep. So if you say anything weird, are we to take it that you're...
I take full responsibility for all my own
Excellent, good. No excuses.
No excuses.
Good. So you just told a room full of people that all do combustion testing that we are perhaps not focusing on the right things. And I love it when people say things that are inflammatory. Will you explain what you mean by that?
Sure. So a lot of the combustion safety testing is focused on this one particular test called depressurization. So the concern here is a valid concern, which is that as we have tight homes, when we start sucking exhaust gases out of those homes, just any kind of exhaust, this could be your bath exhaust, your dryer, your range hood, if you happen to have a range hood that exhausts, which we can talk about later. Mm-hmm. We start pulling air out of the home, then the idea is you're pulling against that natural draft appliance. So some gas appliances have fans in them to help induce draft, to help get started, but most of them rely on the hot exhaust gases that are going to want to rise up through the vent to pull air up behind those hot exhaust gases up from the house so that all that exhaust, that combustion exhaust, can get out of the house. If you have another exhaust fan in the house, this is not combustion exhaust, this is just air exhausting leaving your house, then it's going to be pulling against that, and then it could pull some of those combustion gases back into the house, and that could be an air quality problem.
But you're saying it's not a problem.
Well, some cases it is a problem. The real question is trying to figure out when it's going to be a problem, because what we do is we do tests that predict or supposedly predict when we are going to see a problem. And I think sometimes those tests predict that things are going to be a problem that in real life are not big problems.
And for anybody who's not taken the BPI exam, the worst case
there are
test...
people who have not taken the BPI exam.
If you haven't received a free training from your local municipality or the utility and taken advantage of that. Okay, so if you haven't done one of these, it's called worst case depressurization. And you're saying that the worst case is...
First of all, it's not worst case. Okay, that's the one thing. It's an induced worst case. It's a good analogy. Remember when the financial institutions, we almost had a complete meltdown of the entire financial system?
What?
Yes. I know. For all the people who are very busy fixing homes, they might not have noticed, but there's a place called Bear Stearns. And anyway, basically, what these tests do is they try to create the most challenging situation that we can think of. And that challenging situation is that they turn all the exhaust fans on in the house at the same time. And the idea is that's supposed to challenge the system to see how much do you depressurize the house when all the exhaust fans are on. With the idea that you could potentially have that situation come up. And if that's happening while your appliance is running, and the appliance doesn't have enough draft, enough force that those hot exhaust gases going up to overcome that depressurization, then the exhaust gases from the appliance would not vent, they would be pulled back into the house. So that's the worst case depressurization. And we have a lot of issues with that test. One of which is that it's creating a situation that doesn't very commonly happen. Okay, and in order for these exhaust gases coming into your house, in order for that to be an air quality problem, there's really multiple things that have to happen. The first is enough of these exhaust gases have to come into your house, and they have to have enough pollutants in them. So just because it's the exhaust from the appliance doesn't mean it's full of pollutants.
It is full of moisture.
It is full of moisture.
Bad stuff in general, but not necessarily carbon monoxide.
It's not necessarily full of bad stuff. It is necessarily full of moisture.
You're a scientist, so I assume you know. What is actually in there? I know moisture.
That's a great question. So if everything's working as it should, everything's working perfectly, the products of combustion will be carbon dioxide and water. water vapor. Now, if you have a big 100,000 BTU per hour or 150,000 BTU per hour furnace, okay, that's producing enough carbon dioxide and water vapor that you don't want that amount of CO2 and water vapor in your house, period. Okay, so
because most people don't realize, but the symptoms of carbon dioxide poisoning are the same as carbon monoxide poisoning, right? You can just you just express it out when you go out into fresh air.
Yeah, more or less. So it's basically you could get to an oxygen deficiency situation. Carbon monoxide replaces the oxygen carrying. It replaces oxygen in your blood, essentially. So your blood doesn't efficiently carry oxygen. You could create a situation where you actually have an oxygen deficiency in your home. That's fairly rare to get that high of a concentration. But CO2, you would get like a lightheadedness. If you get thousands of ppm of CO2, that does cause symptoms that, as you say, are similar to some of the CO symptoms at low levels. But the water vapor would be a problem too, right? So now the CO2 would be an acute problem that would not be good for you right now. And the water vapor is a problem if it happens over time, then it's going to create moisture problems in your house. We never want a big appliance dumping its exhaust gases, but it's not very common that happens, and it's pretty easy to. You don't need to do a worst case depressurization test to see if that's going to happen. Our real thing is our real primary interest is in prioritizing the hazards. So figuring out what are the most important hazards, and making sure we're doing the right test to see those.
So what we have already ruled out is that because it's reached so seldomly. Now, you showed all kinds of graphs and everything that it's going to be impossible to try and recreate on the radio. But can you just give us the basic overview of what you found when you studied these phenomena?
Yeah, so there's really, this is going to almost sound philosophical, but there's really two issues here. And there's a physics issue in terms of certain physical things are happening when an appliance backdrafts or spills exhaust into a house and pollutants get formed. And then there's the statistics of how commonly those physical features come together, right? So on the physics of it, what we're looking at is, I have to take a step back and explain what happens with the drafting. So the physics of the drafting, how you establish draft, the factors that go into that are how big of a burner, so how much heat are you producing, and then details of the ductwork, because you can lose some of that force working your way through a complicated set of
like the flues, you mean?
The flue, right? Okay. So this is the vent, okay? Well, the terminology is a little confusing here, right? So generally, we refer to the flue as the piece that's attached directly to the appliance. Okay, so if you think about a storage water heater, the pipe that comes up from the middle, that's the water heater flue, okay? And then the vent is the thing above that carries the exhaust gases to the outdoors. Okay, so that's the terminology we're using here. It's a little tricky because there's something called a direct vent appliance. And in a direct vent appliance, it actually refers to getting combustion air from outside as opposed to inside. So it's thoroughly confusing with the terminology, but hopefully your listeners,
they should be pretty
BPI or non-BPI trained listeners are familiar with this. So in terms of the venting, the size of the appliance matters a lot. The outdoor conditions. So it's a temperature difference. It's basically this idea, we say hot air rises. Well, hot air doesn't rise. Hot air only rises in relation to air around it that's colder. So the hot air is less dense, okay, than the cooler air around it. So the less dense air is going to move up relative to the more dense. So if you have a situation where it's the hot, basically the warmer it is outside, the less draft you have, because the outside conditions are not as different as temperature, not as much different as the temperature of the gases that are coming up out of the vent at your roof line or above your roof. So it's how big your appliance is, so how much energy you're producing, what's the outdoor condition, and then what are the details of your venting system, right? So some vents have more heat transfer, so by the time the exhaust gases get to the outside, they're not as hot. Some are well insulated. If it's like a brick brick fireplace, brick chimney, okay, and it doesn't have a good liner, then that will affect your draft as well because you'll lose a lot of heat to the outside. So it's the size of the pipe. So that's your draft. And then the other issue is how much you're pulling on the other side, and that's the depressurization.
And your point is that the bigger the appliance is, the harder it is to get it to backdraft.
That's right.
And the smaller it is, though, the less it's producing.
In general, that's the case. Now, there's another thing though where the amount of there's the physics of actually drafting, and then there's some physics of the actual pollutant formation. So I started saying if everything's going well, you have carbon dioxide and water. You form another thing that forms during the combustion is these things called nitrogen oxides. So that's not it's a pollutant, it's a trace constituent, but it doesn't necessarily mean that anything is going wrong. And if everything is going right, all of your nitrogen oxides will be emitted in the form of nitric oxide, NO. But sometimes some of that NO gets converted to NO2, nitrogen dioxide. And that's actually an important distinction because the nitrogen dioxide is a respiratory irritant and is a regulated pollutant.
And that's something that the EPA actually has standards on for outdoor air, as you were pointing out.
They do. And then the other thing, of course, that people are more familiar with is carbon monoxide, CO. So when CO forms, that's the carbon in the fuel has not oxidized all the way to carbon dioxide. So it's very common to have little bits of CO, but if you have a lot of CO, then there's something wrong with the combustion. So there's a physical problem with the combustion, and that might be that the burner is not adjusted properly. So it's like putting too much fuel into the flame. So it could be a broken regulator. It could be a problem with the air supply. So people like to think about the combustion ventilation air, or CVA, how much air is coming into the house or into the space that needs to be combusted, but sometimes it's actually just at the appliance. There's some blockage with the air coming into the combustion space.
And just to clarify, you are not advocating that people go around punching a hole to outside in all of their mechanical rooms, right? That's not the fresh air that we're talking about, that a lot of code departments might misunderstand.
Well, it's interesting you should say that, because one of the fixes one of the ways to make the combustion systems more robust is to, quote unquote, put them outside. And I just made quote signs with my fingers. So
you couldn't hear that.
You couldn't hear that, so I had to say that. So a common situation is in a lot of places in the country to have the appliance be in a closet that's inside the living space. Okay, and now I'm not sure if it's everywhere, but I think most places, if not all, a closet. This housing, that appliance would need to be ventilated. It would need to be connected directly to the outdoors with low and high openings.
Or to the indoors, right? It just needs to be ventilated to something.
No, I think I think in most places now, that I may be wrong about this. You should check. Maybe one of your listeners can write in. But I think those combustion appliances, I think in most states, if not all, because I think it's part of the International Mechanical Code, are required to have high-low venting to the outdoors. Okay, so their combustion air would have a good. They might be able to get away with in some places combustion air coming from the indoors, but they have to be vented to the outdoors. So it is a good question. But one very safe way is you can seal that closet from the inside. So you close off all the openings to the inside, and you punch a hole to the outside from that closet, so that the combustion air, make sure you get plenty of air for combustion coming from the outside. The appliance then vents to the outside, and that whole closet now is separated from the indoor space.
Mm-hmm. But to get back to the issue at hand, you're saying that none of that stuff actually is that important, because you found out through your studies that this stuff really is a drop in the bucket, and there's bigger fish to fry.
Well, if I may disagree with the host,
please.
I wouldn't say we found that. What I would say is that we found that there's too much attention paid to these worst-case depressurization tests, with the idea that everyone is very concerned about people dying of CO poisoning, which actually doesn't happen all that often, but that's another story. But
Allegedly, doesn't happen all that often.
Well, as far as we can tell, it doesn't happen that people die from CO poisoning from natural draft appliances. Okay, so and when they do, what the common feature is that usually there are multiple things that have gone deeply wrong. So it's not just because a furnace or water heater backdrafted; it's because the furnace or water heater was very badly broken, and usually it had some serious defect with the venting system. So it wasn't a backdrafting issue, it was a venting problem. So, for example, we really commend those programs and protocols that pay attention to inspecting the venting. So looking to make sure that the vent from the appliance all the way out through to the outside is connected, has integrity, doing pressure checks, doing draft checks to make sure that the exhaust gases are being pulled into the vent. Inspecting the burners. So as much as possible, some appliances is harder, but a lot of them you can actually see. To look and see if there are carbon deposits, for example, that would be an indication that there's a burner problem. Make sure that the air supply to the burner is not clogged. And to check the emissions of the appliance. So there's handheld combustion safety analyzers. You can, the vast majority of appliances, if it's an appliance that can easily leak or spill exhaust gases into the house, then there's a place where you can measure the CO in the appliance exhaust. And if you do that and you find air-free is a way we measure this, so we basically put it all in the same, it's a good apples to apples comparison because these appliances have different amounts of extra air. So unless you know how much extra air it has, then the same CO reading with twice as much extra air, it doesn't mean the same thing.
When you say extra air, you mean, for example, a huge 100 or 150 kilobtu furnace is going to be pushing a lot of air through its flue. And if there is...
No, the extra air is that the appliances operate with excess air. So basically there's a certain amount of air that they need for combustion, and they bring more air than that through the combustion chamber. Okay? And it varies by appliance. I think for water heaters, a typical classic storage water heater, it might be 30%. Someone could correct me, but I think 30%.
You're not talking about the oxygen reading in the leftovers in the combustion gases.
Well, so you would actually see that if you had a combustion analyzer and you were looking at the oxygen. So if it was perfect, exactly stoichiometric combustion or exact mixture of air and fuel, there would be no oxygen left in the exhaust from the appliance. But if you look very often, there is some oxygen in that exhaust, and that amount varies in terms of how much it is. But since that amount varies, we adjust that reading back to the situation of no excess air, air-free. So that's the air-free carbon monoxide or air-free NOx could be.
So you're recommending always use the air-free setting.
The air-free number is just a more fundamental intercomparable number, so we like that number better. We don't have to worry about how much extra air there is. We just go to the air-free. And most combustion, I shouldn't say most, but there are many handheld combustion analyzers that will do that calculation. It will measure the excess oxygen. It measures the oxygen, which in exhaust is all excess, and then it makes the adjustment back to air-free. So by measuring the CO, the carbon monoxide air-free in the exhaust, you can get a pretty good indication of whether the burner is working properly. If the burner is working properly, that number should be very low. If that number is in the tens of ppm or even sometimes in the hundreds, it could be okay. When you start getting up into many hundreds to 1,000 ppm, that's an indication that something's not right. And that could be, again, that the burner is overfiring. It could be that there's a problem with the air supply or some other things.
And that's when you're saying there is clearly a problem we should investigate.
So that's when you start investigating, right? So one of our issues is some of the test protocols, out of the good intention of being extra safe, extra cautious. Thank you. Will set very low thresholds for failing an appliance for carbon monoxide. So in California, for example, there are some of the regions the appliances will fail if they are a water heater or a furnace if they get to 101 ppm of carbon monoxide air free. So that we think that's too low to fail the appliance. That it's not it's an indication something's not working perfectly, but it's far below being a problem, especially for a situation where you have a small appliance in a big house. So the other part of the physics is that small appliances produce smaller amounts of exhaust gases, and big appliances produce bigger amounts of exhaust gases. Makes sense. And by big and small here, I'm talking about BTUs, not physical size, right? Basically, what we want people to do is we want people to pay attention. We want to help the industry develop standards that pay attention to these physical features, which is the appliance that we're concerned about. How big is it? How much exhaust gas is it producing? How high does the CO need to be to create a truly hazardous indoor air quality problem in a home? And the bigger the home is, then the appliance needs to produce more CO. And then the other piece to this is on the airflow that's required to produce this depressurization. I'm going to take a breath and then I'll get back to that.
So now you built a simulator that kind of will tell you statistically how often this scenario, this potentially hazardous, sick-making or death-making scenario is going to happen, right? Is that something that the public has access to?
We do have a simulation model. The simulation model doesn't actually do that yet. We will be doing that. Okay. So getting back to the depressurization, let me finish that point actually, because I think it's a relatively important one, which is we have this model, we being a lot of people in the industry, including myself before I stopped to think about it, frankly. We air seal these homes to be very tight. Now we have a nice tight home that doesn't have a lot of ventilation. So we have to be very careful about any pollutants that get admitted into that home. Absolutely. And then that home that's tight, if we depressurize, then we could pull exhaust gases from the appliance into the home. Okay. What we don't always think about, what the standards don't consider, is how much airflow is required to depressurize. So if you have an induced draft furnace, for example, the threshold, the depressurization threshold to fail a depressurization test is 15 pascals. So you have to depressurize to 15 pascals. Well, if you get a reasonably tight home, you can have some big exhaust fans. Maybe you like to cook a lot, so you have a big kitchen fan. Maybe you have a 350 CFM kitchen fan, and you have a 200 CFM dryer, and you have a couple of bathrooms. So you turn all those, and before you know it, you're up to 650 CFM of exhaust flow out of your house. Okay, well, it might be if your house is tight enough that 650 CFM is enough to cause 15 pascals of depressurization. Or let's just say 5 pascals of depressurization. Okay, so then you would fail your appliance because you pass your depressurization limit. What is not being accounted for is that 650 CFM of exhaust out of the house means that 650 CFM is coming into the house of air from the outside. So that's dilution, that's ventilation. So that's no longer a tight house. That's a house that is being ventilated with 650 CFM of ventilation flow.
And to clarify your own point earlier, once you get a house under 2 air changes per hour at 50, then that's actually not ventilation because all the air that's coming in is through the chimney at that point, right? You made the point that really extremely tight houses...
Wherever the air is coming in is ventilation air. So if you have 650 CFM coming down the chimney, regardless of how tight it is, you have 650 CFM coming from outdoors... Mm-hmm. That 650 CFM is diluting whatever pollutants are being emitted into the house.
I love it when you say inflammatory things.
How is that inflammatory? It's physics. There's nothing inflammatory here at all. This physics.
But you're just making something that we thought was very simple and we could just do our jobs, and now you're saying, well, it's actually more complicated than that.
Well, it is more complicated, and there's a real challenge. So it's easy for me as a scientist to criticize, and I recognize that the challenge is coming up with protocols that are robust, that you don't need to be an air quality scientist to follow, that you don't need to spend hours making calculations or running simulations. We've realized that. So we realize that we need to, at the end of the day, put up or shut up. We need to come up with something that is as simple as what we currently do, but is better. And that's what we fully intend to do. So this is a challenge we recognize that we're going to take on to try to come up with alternative suggestions. So for right now, what I always tell people, I give these talks. People say, oh, wow, I never knew. Thank you for telling me this. What should I do differently? And I have to keep telling people, nothing yet. It's not entirely true. There are some things that people should do differently, and I'll get to that in a moment. But the basic idea, though, is that we want to look at the physics. And the statistics part of it, just to close, because you asked about the statistics is trying to understand how commonly we have these multiple exhaust fans operating to produce these flows that could depressurize a house. And also, is there enough duration? So it's not enough that, 3 times, if it happens where 3 times a year all those exhaust fans are on for 20 minutes, okay, it doesn't matter if I'm backdrafting for those 20 minutes or spilling all my exhaust, because there's not a lot of damage that's going to happen in those 20 minutes. Okay, what we're looking for is situations where there's a backdrafting and spillage is going to persist for hours, generally many hours, but at least 1 to several hours, and then there needs to be enough pollutants coming into the house during that time to raise concentrations up to a hazardous level. And the only way that happens is if there's not too much dilution flow. So there's a lot of things that all have to come together. And the current standards aren't recognizing that. They're not recognizing, that all these physical things have to come together, and that when they do come together, there's a built-in safety mechanism of the extra dilution. And then there's basically a statistical probability or improbability. So one of the things we want to do is actually treat it more like a risk management or risk mitigation problem than a pass-fail problem. So we want to say basically, what's the likelihood? And it might be that we calculate for some situation that there's a 1 in 100 chance that once per year this is going to happen. And that if it does happen, there's a 20% chance you could get to 20 ppm of CO in your house. Well, no one wants to have 20 ppm of CO in their house, but if there's a 1 in 100 chance that's going to happen once a year, and then a 1 in 10 chance that you're going to get to, I don't remember what numbers I threw out, but you start getting to where there's a 1 in 1,000 chance that it's going to happen once a year, and now I tell you, I think you need to spend $1,000 on a new power vent water heater to fix this problem, because there's a 1 in 1,000 chance that once a year you could have 20 ppm of CO in your house. I think that would be a lot different consideration that someone would have than right now where the industry is saying, you're going to die. So you got to fix your water heater.
I was assigned to tell Keith Aldridge, who was on this podcast last time, what you said in your session, because he had somewhere else that he needed to be. But I basically told him what you just said. And he said, so he's in favor of us getting rid of seatbelts, right? And I thought, well, no. And he said, well, really, statistically, though, seatbelts don't really save that many people. So it strikes me that there are probably a huge number of things that the government adopts some kind of standards on that say that, like, really protect us from that 1 in 1,000 chance. So how is this different than seatbelts, as an example?
Well, I'm still it's a good question. So I don't know the statistics of seatbelts. So yeah. I would question. Car accidents are pretty common, and when you're in a car accident without a seatbelt on, you get hurt, and you get hurt very severely generally. So I don't know what the statistics are. Just from my own experience, I know lots of people who have been in car accidents. And I bet you do too, and I bet a lot of your listeners do, okay? And they were wearing seatbelts, okay? And if they hadn't been wearing seatbelts, I bike, okay? I wear a helmet, right? Well, I was in one accident in my entire 25 years of biking around cities, okay, where my helmet came into play. But I'm always going to wear my helmet, right? It's a cheap thing to do, okay? And the risk is catastrophic. I'm all in favor of doing cheap things to screen for safety measures for catastrophic risks. Okay, so absolutely, I'm all in favor of going and taking a look at every gas appliance, even if you're not doing anything that's going to affect it at all. If you're a home performance contractor, you're a home performance contractor. Part of home performance is safety. So there are combustion appliances in the home. They do present risks. I think it's worth at least taking a look. See if there's any obvious problem. Looking to make sure the vent is connected is a really good idea. Looking to make sure that the burner doesn't have really high CO is a really good idea. What's interesting to me, though, is we pay so much attention to doing many factors of safety on the vented appliances. And yet, as a society and even as a home performance industry, we pay less attention to other risks, including combustion safety risks that are much more commonly causing problems. And go ahead and ask me.
Like what? Was that good?
Perfect. Well, there is an there's an appliance that is in many millions of homes. I think it's something like half the homes nationwide. Okay, some places more. That we allow to spill a gas appliance. We allow it to spill into the house 100% of the time.
It's not a vacuum cleaner, is it?
Not a vacuum cleaner. It's a gas appliance. You're the interviewer.
What kind of vacuum cleaner do you have?
Put that video game away. Come on back to the interview.
Is it in the kitchen?
It's in the kitchen. So it's your cooking burners. So if you have gas cooking burners, now some homes have vented range hoods above the cooking burner, but you have to turn those on. And I know from my own research, we've done research on this, that a very small percentage of the population uses them every time they cook. A larger percentage uses them sometimes, or at least they say they do. And I think more and more people I've been beating this. So if you're listening, make sure if you cook, you have a vented range hood and you use it every single time. There is no reason not to do that. Okay. But we've done research into this. We've done both simulations to predict how commonly there are problems, and we've also done measurements in homes, and those two things line up pretty well, actually. And what we see is that in homes where there is a gas cooking appliance, commonly people don't use the range hoods, and they have elevated pollutant concentrations that are associated with the gas appliance. And some of the industry protocols, getting back to the combustion safety protocols, some of the industry protocols do look at the emission rates from those kitchen appliances, although there's some imperfections there as well. But they don't require the venting. So we allow the cooking burner to spill, to backdraft, if you will, and spill. It's not really backdraft, but it spills exhaust into the home 100% of the time. Do we go over time?
No. I just got a call. Hang on 1 second. Just hold that thought. Okay, good. Okay, so you were saying we allow them to spill 100%.
We go crazy on the water heaters to make sure that under no circumstances could there possibly ever be any water heater exhaust coming in, which is not exactly true because the test does account for some intermittent spillage at kind of at startup. But then the cooking burners, we say, well, people are on their own to figure that out. And I don't think that's a good idea because, again, we see it. Through the simulations, we come up with estimates that in homes that cook with gas at least once per week, okay, that accounts for the variations in cooking, and don't use range hoods, which most people don't, or use a vented, have some kind of venting in the kitchen. We estimate that it's something like 5 to 8% of those homes will have, in a typical week in the winter, will exceed the outdoor air quality standards for carbon monoxide. Okay, and for nitrogen dioxide, it's something like 50 to 70% of the homes will exceed the outdoor air quality standards. So there are very commonly problems, we believe, from these cooking appliances. We've done some measurements. The measurements more or less back that up. It's a little harder with the nitrogen dioxide because you can't measure it in real time very easily, so we have to take integrated measurements. But basically, we see in homes that have gas cooking, we see substantially elevated concentrations of carbon monoxide. Carbon monoxide in fewer homes because not all cooking burners produce carbon monoxide, although cooking burners in general produce more carbon monoxide than other types of burners. Ovens very commonly, again, your listeners, we were just on to session. Every time I do these things, I ask, okay, how many of you who measure emissions from appliances have seen 1,000 ppm CO in a water heater? And one or two hands go up and say, I saw one. And I say, okay, well, how many water heaters have you measured? 500, 1,000, 2,000. Okay, so it's a very small percentage. And then I say, okay, how many people have seen 1,000 ppm in an oven? and then everyone's hand goes up, right? So it's much more common. And the cooktops we don't even really test in the right way because having a pot on top of the cooktop changes the flame and it changes the CO production or CO release. So holding your wand over an open flame doesn't give you a relevant measurement for when someone is cooking with a pot on that burner. So that's one
area. Or cooking with a big roast in the oven.
Right. So that's one area where we think the test methods, first of all, they don't adequately check for the appliance, and secondly, we don't require the venting. Now, there are some states that do require venting in new homes. So California, Washington, and some others. The ASHRAE ventilation standard requires,
which is referenced by some codes.
Referenced by state codes, exactly. Energy Star requires kitchen exhaust ventilation, so a new Energy Star home will have that. But for the retrofit, it's not required to install kitchen ventilation if it's not there already.
Now, here's my biggest question for all this. Hang on one second. I just want to make sure. Here's my biggest question with all this. These standards that we're talking about have been around for years, and the National Laboratory, which, you work for one of them, there are multiple national laboratories, and you guys are all brilliant scientists. Why are we coming up with these standards, and then why do you have to come along after the standards already have been written and find out what is wrong with them? Why don't we just ask you to develop the stupid standards in the first place?
Well, some very smart people developed these test methods. What's really interesting is when we got back into this field, we've been off and on working on this field, Lawrence Berkeley Lab, for years. And we got back into it recently because we were seeing that there was a sort of a reemergence of this issue with the air sealing. So there was a big push for air sealing. And then what we were seeing is two things. One is that a lot of homes were failing combustion safety tests. Is it okay if I give you a slightly longer answer here? I will get to the answer to your question. No. But they were failing these combustion safety tests. And then they were requiring that resources be spent on fixing the combustion safety quote-unquote problem. Again, those hand quotes there, finger quotes. Or they were not doing air sealing because they didn't. The contractor could predict that they were going to fail a combustion safety test.
So they aborted.
If they aborted, right? Yeah. So they aborted the test. Okay, great. So we said, okay, well then there's a lot of money being spent, and there's a lot of energy efficiency opportunities that are being cast aside. So we looked back. We said, okay, well let's see, what's up with these tests anyway? And one of the interesting things we found is that the very people who developed these tests found through their research that the tests were not very good predictors of problems in real life. Now, there's a big caveat there, and here's the big caveat, okay, is if you're looking to see if a test you are doing is going to predict whether an unlikely event is going to happen, then you have to do a lot of monitoring to see if that unlikely event really does happen. If I do a combustion safety test in a certain way to say, I'm going to find situations where, a dozen times a year, this appliance is going to spill its exhaust gases into a home, then I would have to monitor for a whole year and see if it really happens 12 times, right? Or how many times it happens. Well, that's very expensive, doing a year's worth of monitoring in a home. So there was never the money spent to verify that these tests were accomplishing the goals that they set out. So even from the start, and the little bits of money that were spent where they did shorter term testing, which it didn't give a certain result, but the indication from that result was that these tests were probably failing a lot of appliances that were not actually going to be a problem, but they couldn't for sure say because the monitoring wasn't happening for long enough. So it's a little bit of a difficult situation because how much is it worth it to the industry and to the nation to answer this, and how expensive would it be to answer this question? I could design a study and answer it, but it's very, very, very expensive to do it the sort of straightforward way. So one of the other things we're doing is trying to think of how we can use simulation, how we can measure a relatively small number of parameters to give us the bits and pieces of information that we can put together to answer this question. It's not really an easy answer.
But you will have an answer for us sometime in the
hope
future.
so. I'm trying my best.
All right. Brett, thank you so much for being on the show.
Oh, my pleasure.
Brett Singer is an indoor air quality scientist at Lawrence Berkeley National Laboratory. You've been listening to the Building Performance Podcast from Green Dream Group in Chicago. I'm Corbett Lunsford. Tune in next time.